Language models, LMs, particularly large language models, LLMs, have wide range of applications in financial field due to its ability to analyze and model textual and multimodal data. However, LMs are not perfect. They sometimes hallucinate and may generate non-factual responses or produce non-causal reasoning points. These errors, particularly in finance filed, could lead to incorrect conclusions and monetary losses. Hence, we need some robust mechanism to detect factuality and causality issues that may emerge in self-reasoning process of LMs. Here, we analyze the feasibility of using NLI as a judge to automatically detect such issues. Natural language inference, NLI, is a classic NLP task that checks whether a hypothesis follows logically the premise, aka entailment versus contradiction versus neutrality labels. Here we focus on entailment versus contradiction. For factuality issue detection, the premise is the information input into LM and the hypothesis is the reasoning point. For causality issue detection, the premise is the reasoning points while the hypothesis is the LLM's final decision or the classification output from LM. For factuality issue detection, we want to check whether there is factual inaccuracy for each reasoning point given the premise. For causality issue detection, we want to check whether there is logical inconsistency. For example, negative attributes are described as contributing to positive classification for each reasoning point. This page shows the experimental setup. For dataset, we use German credit dataset, which is a public benchmarking dataset widely used in financial modeling. For NLI tasks, we consider a group of encoder models such as DeBerta v3 large, BART large, Roberta large. We also consider a group of LMs such as Llama 323b, Llama 318b, Gemma 22b, Gemma 29b, Phi35 Mini, Phi35 Mo E, GPT-4o. For both encoder models and LMs, we experimented with both the pre-trained version and fine-tuned version. We mainly consider these performance metrics: AUROC, AUPRC, F1 score, and accuracy. We leverage Wilcoxon rank sum test to reflect the statistical significance on any observed difference between two groups of experimental outcomes. Let's look at the performance of pre-trained encoders and LMs on checking the factuality and causality errors. In each figure we have two lines. Red dotted line is for the entailment probability density distribution for reasoning points without error and blue solid line is for the reasoning points with error. Top row is for factuality error detection and bottom row is for causality issue detection. In this page we show the comparisons with DeBerta v3 large, Phi35 Mini and Phi35 Mo A as example. On this page, p-values for the detection are listed. When p-value is smaller than 0.05, that means the encoder or LM has the ability to distinguish reasoning points with V's without factuality or causality errors. Similarly, this page shows the entailment probability distribution and p-values for fine-tuned version of encoder or LMs. We can see that for all the tests shown on this page, p-value is smaller than 0.01. Which indicates these fine-tuned encoders or LMs have the statistical ability to distinguish reasoning points with V's without factuality or causality errors. This page lists out factuality detection results of pre-trained and FPFT encoders and LMs under NLI paradigm. We can see that fine-tuning enhances both encoder models and LMs' ability to detect factuality issues. We can also see that LMs underperform compared to encoders in factuality issue detection. For example, FPFT DeBerta v3 large has AUPRC 0.92 while the best one across LMs is only Phi35 Mo E at 0.86. Similarly, this page lists out the experimental results for causality issue detection. Again, LMs underperform compared to encoders in causality issue detection while fine-tuning can enhance both sides of the model's ability of issue detection. For example, FPFT version Roberta large has AUPRC of 0.94, where the best from LMs is Phi35 Mini at 0.92. In this page we try to use rank sum test to compare the discriminability of pre-trained and fine-tuning models. Here, a smaller p-value indicates better discriminability. In the bar chart are the difference in p-value between pre-trained model and the fine-tuned model. We can see that consistently, p-value of the pre-trained model is higher than that of the fine-tuning model, indicating that fine-tuning can enhance the model's issue detection capability. In this page, we try to assess whether fine-tuning can mitigate self-evaluation bias. Self-evaluation bias refers to the systematic tendency of LMs to incorrectly judge their own erroneous reasoning or that of models within the same family as correct. To quantify this bias, we applied the Ranksum test to compare the entailment probability assigned to the erroneous reasoning points from same family of models versus those from other type of models. The null hypothesis is that there is no difference on the entailment probability between the two groups. The alternative hypothesis is that the entailment probability assigned to the erroneous reasoning points generated from same family of models is higher than that on the erroneous reasoning points generated by other models. This figure shows the differences of p-value difference between the fine-tuning models and the pre-trained counterpart. We see that in most scenarios the p-value difference is positive, indicating fine-tuning effectively mitigates LM's self-evaluation bias.